let's start with evaluation today. And I will start with a brief presentation of myself, very brief. So I did my bachelor and master in mathematics at the University of Padua. Then I also did a PhD there in information engineering. And then I moved to Copenhagen, where I'm now an assistant professor. And the important thing for you to know is that I attended this school in 2015, and it was a very, very nice opportunity to meet both lecturers, but also other PhD students. And with PhD students I met there, I'm also in contact. Still now we see each other at conferences. We are very happy to meet every now and then. And we have one here, the organizer. So that's a good opportunity for you to be here. And what are we going to talk about today? We'll go through the Cranfield paradigm for evaluation. We'll go through some evaluation measures and user models, and a bit more on other topics in IR evaluation. So what is the aim of evaluation? Why, first of all, do we need to evaluate? Well, if we can measure something, we can improve it. So evaluation is very important to understand how our systems perform, but also to improve them. And what are the criteria for, let's say, having good evaluation? So it should be valid, scientifically speaking, which means that we need a valid methodology in terms of measures and statistical tests that we use. It should be large scale enough, so it's realistic, and it must be repeatable. So if we repeat the same experiment, hopefully we would like to get the same results, even though sometimes it's hard. And the task and use cases that we consider in evaluation, they should be realistic in the sense that we always need to keep in mind what is the specific task or the specific research questions we are addressing, and try to use proper evaluation to show what we really want. And it also needs to be understandable, especially if you are in a context where your audience or your client is not an expert, right? So it needs to be easy to understand. So what do we evaluate? Well, we can evaluate the efficiency of our system, but what we will focus on today is the effectiveness. So it's more related to the user satisfaction. But talking about efficiency, how do we evaluate efficiency? Here you just have a very brief overview. So usually you can look at the index, for example, the time it takes to build the index, the space it takes to generate and store your index. And then you can also look at other criteria, like, for example, throughput. How many queries can your system process in a given period of time, or query latency, how much the user needs to wait to get a result. Nowadays, you can also look at the training times or time to fine-tune your models, and also the carbon footprint. So what is the amount of greenhouse gases that you produce when training, doing inference, and so on. All of these, usually, they're not very interesting for the users, except for the query latency, and maybe nowadays also the carbon footprint. But usually when you measure efficiency, it's more on the system side and the application side. So you want your system to scale. But today, as I said, we will not focus on efficiency. but we will focus on effectiveness. So there are different ways you can evaluate your system, and here we have a representation of these ways. I don't know if I can go too far from the microphone. So we have on the left side what we call the system focus here. So basically, that's where you evaluate your system with track style studies. Today we will mainly focus on this part. So you don't really have the users involved in the evaluation. While on the other side of this spectrum, we have the human focus. That's where you also involve the users and where you can conduct, for example, some user studies. You can interview the users. You can get feedback from the users. And these are usually smaller scale studies because you cannot afford to have a very large user studies. And then in between, we have something about, for example, log analysis, where you maybe have a system that it's running online and you collect some log data. And then what you do, you analyze this log data, for example, to understand how the system is performing. But as I said, today we will focus on the track style evaluation. So what is that? It's based on the Cranfield paradigm. And it's dated in the early 60s. But basically, it's a very simple concept. So you need an experimental collection. And what do you have in an experimental collection? You have documents. And this also, it's called sometimes corpora, the set of documents. You have topics or queries. Topics, sometimes they are expressed as an information need. So it's not only a query, but for some cases, you also have a description of what the user is actually looking for, and then a short query or a short question. And then you have relevance judgment. So they can be graded or binary. And these are relevance assessments. So for each query and document pair, ideally you want someone, the user, to tell you, okay, this document is relevant or not for this query. And why do we use test collections? Because then we ensure comparability and repeatability. So when you use the same collection for different systems, you make sure that the base is the same for all the systems and that you can have a fair comparison. Now, how does it work in practice? Well, we have a topic, as I said, or a query, and then our system generates a run, so a list of documents, and then through relevance assessment, so we need someone to tell us, okay, this first document here, it's highly relevant for this user. So we need this assessment. Once we have this assessment, we usually convert them to some weight. It can be 0, 1, or it can be graded, as I said at the beginning. And then we compute a measure on top of this list of numbers that we eventually get. And this is repeated over all queries and overall documents. So how much does this process cost? Let's assume we want to compare just two systems, A and B, and we have 200 queries. And we just want to compare the top 10 documents because we say, okay, the user just looks at the first page on a web search engine, so we focus on 10. And then let's assume that the time to annotate, assess each document is 30 seconds. This is very optimistic because sometimes you have long documents or queries that are hard to assess. Then if we do like the multiplication, so we have 200 queries, 10 documents per queries, 2 systems. Turns out we need to assess 4,000 query document pairs. And if we assume it takes 30 seconds per query document pair, then it's going to be around 4.2 days, assuming that you have one person assessing documents the full day, 8 hours per day without doing anything else, which is not scalable if you think about this, because it's just 2 systems and only 200 queries. So how do we solve this issue in IR? We have large-scale evaluation initiatives. What's the point here? You group many researchers, many group of researchers that work on a task. It can be a ranking task, but can also be with slightly different objectives. And then each group submits some rankings, and these rankings are somehow merged. We will see how is that. And only some documents are assessed. And they are assessed by annotators that are hired through these large-scale initiatives. So these are the main ones currently running. So we have TREC in the US, NTCIR in Asia, in Japan, CLE in Europe, and FIRE in India. So how is the assessment done? So let's now assume you have 2 rankings, 2 lists, A and B. And what you want to create is a pool. So what you do is you take the top K documents for each ranking and you merge them together, removing duplicates. And this is the K that you choose. It's the depth of the pool. So here, for example, here you have take the top 100 for each ranking, you merge them, and for each topic, you create a pool. These are the candidate documents that will be assessed. So not all documents will be assessed by all documents that are ranked in the top by all the rankings, all the systems that you have. So that you kind of try to make sure that you go deep enough so you find relevant documents even further down in the ranking, but you also explore the collection by considering different approaches, different rankings. So to give you a small example, we have 2 systems here, A and B. And this is a question for you. You can discuss it in pairs or groups. It's very simple. Like, let's assume now we want to create a pool at depth 4. So which documents will be included in the pool? And another thing that you can try to think about is that whether this process is fair. So I'll give you a couple of minutes and you can discuss in pairs or groups. Is the question clear? What's the group? So I can see what it is. Yes, so K is depth. So you will consider the top K documents to be included in the pool. So anyone that wants to guess? Yep. So how does it work? We take the first 4 positions, right? Then we take all documents in the first 4 positions returned by both rankings, and we remove duplicates. Do you think this process is fair? Or any reasons why this process is not fair? Yes?
More because they are in both systems were in the top 4 documents, so they should be have more weight than the others.
Yeah, so this is a good observation. So usually, I will not go through this today, but one question is how to select the documents that we will include in the pool. Another question is how, which order should we consider when we assess these documents? Because sometimes when we have large pools, we just have a budget, right? And we say this is our budget, and we will assess documents until the budget is over. And with this model, then you need also to sort the documents in that you want to assess. So you want maybe to prioritize, as your colleague was suggesting, documents that are returned by multiple systems.
There is a question over there.
Yes, let me check. Yeah, so they're asking if it depends on systems order, and I believe this was the answer, maybe. But the generation of the pool itself doesn't depend on the system order. It's just a set. Any other issues here? Yes?
Absolutely. It's not fair because for the system B, we have just 2 items left instead of 4 items with the system B.
Yeah, well, for system B, all the items will be assessed anyhow. So in this sense, it's fair, but it's kind of on the line that for system A, we have this document here, this 7, is going to be assessed because it's returned by system B. And then it will turn out that system A has 5 documents assessed, while for system B, there are only 4. So in this sense, pooling can be unfair because this is a simple example, but there might be cases where one ranking gets much more judgments than other ranking, just because it retrieves a lot of documents retrieved by other systems lower in the ranking. So there has been a lot of research on this. How do we assess the quality of a pool? And luckily, this approach, it's robust in the sense that if you have enough rankings, enough groups that contribute a ranking, and if you have diversity, enough diversity among these rankings, you have quite a robust pool, meaning that if a system didn't contribute to the pool in the first place, it can be still evaluated using these collections. Or if a system gets many more documents judged, still the evaluation will not be affected. So you will still get kind of precise results. This means that evaluation made with test collections, it's not about the absolute score. So it's not about, oh, I have NDCG value of 0.8, my system is good, but it's a comparative evaluation, okay? So it's more about, okay, my system is better than the state of the art. And again, this is because when we use pooling, we cannot afford to assess everything. So all documents that are not assessed are judged as non-relevant. And the final score that you will get of the measure, it's not the precise, the perfect score, right? Because there is some uncertainty there. Any questions so far? Good. So I'll move to the evaluation measures. So now that we know more or less how we get these relevance judgments, the question is, how do we compute that score? So if we go back to the previous slide, right? Now we are somehow in this phase here. So we assume that we have some judgments for our documents. We need to map them to some weight, and we need to compute an evaluation measure. So this is what happens in information retrieval. I will be very brief about what happens in recommender systems, because you had a lecture before. There are some similarities and some differences. So usually in recommender systems, you have a training set, and your model predicts some ratings for items that are not in the training set. And then you have two ways to evaluate your recommender system. One option is to treat the system as a regression model. So you're interested in your system being good at predicting the rating. And one option is you just consider the ranking of items and you evaluate the ranking. So again, what I said at the beginning, you need to think about the user task and what you really want when you evaluate your systems. In this case, the regression, nowadays it's not very interested anymore for many of the recommender tasks, because you're more interested in producing a ranking, not in really predicting whether the user will rate an item 4 or 5. So you are kind of fine if the system it's not very good in predicting the ratings, but if the system is good in ranking the items, that's what you're interested in. But if you go with the first option, predicting the ratings, what you will do, you will get your predictions from the model, and you'll have your test set. All these question marks, these are items that are unobserved. You have a lot of them for recommender systems, so items where you don't know what the user rating will be. And you can compute an error-based measure. So you just compare the prediction with the actual rating on the test set, and you can compute root mean square error or other similar measures. But as I said, this approach was kind of more popular at the beginning of when the first recommender systems were developed. Now, the ranking-based approach, it's more interesting. How does it work? So again, you have the prediction from the models. You have your user. For each user, you can generate a ranking just by sorting items with the predicted rating. And then, of course, you need to remember that you will remove, again, this depends on the task, but in most cases, you remove from this ranking the items the user has already interacted with in the past, because many times you don't want to recommend them again. You go to the test set and you map your items to the ground truth. So the rating that the user assigned. to that item. As this part here, this is basically what happens with the assessors in IR. So in recommender system, we don't actually look for people to assess items if they're relevant or not, but we use the user ratings. And again, you can consider the top K if you want a top K measure. But to give you an example of what happens, how we compute actually IR measure based on this, once you have the rankings, you map the items to the ground truth ratings. Then usually you decide on how to convert them. If they are, for example, on a scale 1 to 5, you can decide to convert everything to binary ratings or graded ratings. Depends also on the measure that you want to use, because some measures, they only work with binary ratings. And it also depends on the ratings, because it depends on the interpretation of these ratings, because sometimes a rating 0 means that the user didn't like an item, but in other contexts, it can have a different interpretation. So if we, for example, assume a binary mapping, then what will happen is that we will convert this list with the ground truth ratings to this list where everything goes to 0 or 1, and all the unobserved items, they are treated as the unjudged item documents in IR. So they just be mapped to non-relevant. Good. So and this, of course, is repeated over all users. So before we were averaging over all queries or topics. Now we do it over all users. Any questions so far? Good. So now I prepared an exercise for you. And it's about evaluation. So this is your exercise for today. You have 2 rankings from 2 systems, A and B, and you need to decide which system is better. I prepared a paper version of this exercise. I will share it online as well. There is one every 2 or 3 people, so please work in groups or pairs. And you have a IR evaluation measures cheat sheet, so you don't need to remember all the equations, but you can have a look at them. And if you have any questions, something is not clear, you can come and ask.
Yeah, I'll stay.
And yes.
Hi, thanks. I'm curious. How does assessing relevance work for Rexis? Like, once you created this tool and you have this binarization, yes or no, how do you assess it?
Yeah, I'll go back to the slide. So, so basically, in recommender systems, you don't have a real assessment. So what you have is here the test set. So you leave out some of the past user interactions and you use them. as assessment. And then the question is how to convert them to actual values like 0, 1, or 0, 1 to 3, 5, whatever. But this depends on the application. Yeah. Any question or any comment about this exercise? How many of you already knew how to compute these measures like average precision or NDCG? Maybe you can raise your hands. Okay, quite a few. So I hope you took the opportunity to try to do it. And the reason is because you understand a lot of things by trying to do this yourself instead of using a library that outputs the number for you. So yes, I see it from online. Now we'll go through the solutions, and you'll also have a bunch of slides that I will share with a detailed description of how you compute this measure. So you can also look at them. This is what you got with the definitions. So first step, we need to map our documents to the judgment and the weight. So here is what you get when you have a binary mapping, so 0, 1s. And this works for all like measures as precision, recall, and average precision. So what do we see here? If we compare system A and system B, basically we can see that system A has 5 relevant documents, 3 at the very beginning and 2 a bit further down, while system B basically returns 1 relevant document more, so 6 out of 9, which is the recall base. But system B, it's kind of worse in ranking these documents, right? So this is somehow reflected when we consider the measures with and without the cutoff. So if you look at precision and recall, recall here, system B, it's considered better than system A. And this is exactly for this reason, because system EB is better in retrieving more relevant documents. And also because we do not consider the ranking with these set-based measures. And the same goes for precision, because both rankings are like considered the top 10, then system B is better. But if we consider the cutoff, so at 5 in this case, right, only the top 5, we can see that system A is overall better, both for precision and recall. And again, this is just because we consider the top 5 positions. So we put more emphasis at the beginning of the ranking. Now, we have here also recall at correct. So this is precision computed at the recall level. So it means precision at 9 in this case. What's the idea behind this measure?
Why 9?
Yeah, so this is precision at recall level.
The recall level in the A is
it's B. It's RB at the recall, it's precision at the recall base. So it's precision at 9. It's our assumption, basically.
The whole collection, not in the one system.
Yeah, exactly. So the recall base, this is an important point. The recall base is computed on the whole collection, okay? So it's a number that it's represents, ideally, again, the total number of relevant documents that we have in the collection. Unfortunately, because we do pooling, this is only an estimate, because the only way to know exactly the value of the recall base is to touch all the document pairs, which is not affordable. So why do we want to compute precision at the recall base cutoff? This is to make sure that precision ranges between 0 and 1, because if we compute precision at 10, but we only have at most 9 relevant documents, even if we fill the ranking with all the relevant documents, what we will have is 9 over 10. So then it's not possible for the system to reach 1 of precision, right? So it works if you want to compare different systems, but somehow it's can be a good idea to consider the recall base for interpretability of this course. And then finally, we have in the last row a reciprocal rank. This measure only looks at the first relevant document return and takes the inverse of the rank. So it doesn't really matter how much relevant documents are there, how many, and then system A is better than B. A question? Yes?
Yeah, I just have one question on the recall base.
Yes.
So it is total number of relevant documents in the collection.
Yeah.
And we can see the collection, it can be from D1 to D18, right? Because
yeah.
D18, so it should be 18 or because the collection is all the documents. So there are now 18 documents in the whole collection.
Yeah, but like this, the recall base, it's not the number of judged documents, which is 18, but it's the number of judged relevant documents. And I hope it's 9.
Yeah.
Good. So there might be some errors. So let me know if you have something different. Any other questions? Good. So then we can go on with more complex solutions or measures for evaluation. And one of them is average precision. So what does average precision? It takes the ranking of the rank position of relevant documents and computes the precision at each rank position, and then averages by the recall base. So for example, here for system A, we have 1 relevant document at position 1. So precision is 1. Then we have another relevant document, precision is 1. Another one, so precision at 3 is 1. And then we have the next relevant document at position 6. And precision at 6, it's 4 over 6, right? And we go until the end of the ranking, so position 10. And then we divide by the recall base. So again, the total number of relevant documents. And here you can see that if we consider average precision, system A, it's somehow better than system B, right? So even if system B retrieves 1 extra relevant document, because all the documents in system B, they are a bit lower in the ranking, they are penalized. And this is the idea behind average precision. So I want to penalize relevant documents based on where they appear in the ranking. Now, I don't know if you had time to compute average precision at 5, but there might be issues here. And the issue is, how do we normalize average precision at 5? So we use the recall base as in the original definition of average precision, but here we compute at 5. So again, we have a similar problem as before, right? The measure cannot go from 0 to 1, because even if we fill all the first 5 positions with relevant documents, we cannot achieve 1, just because we normalize by 1. So an alternative can be to take the minimum between the cutoff and the recall base. But I have to say that this is a ill-posed question. So usually average precision is computed on the full ranking. So if you have to compute average precision, use the full ranking. Sometimes you will see that at the cutoff, but the measure is really designed to account for the full ranking. And if you really have to do it, then consider the way you normalize the score. And here is an example, basically, of how you do that. So you will see that the absolute score actually changes between the 2 versions, but the ranking of the system doesn't change. So if system A was better for than system B, whatever version you use, this will not change. So it's just, again, for interpretability of the scores that you might want to normalize differently. Then we have DCG and its normalized version. So what does NDCG does? Basically, again, the idea is to consider the position in which a relevant document appears and to discount. The more the document is lower in the ranking, the higher the discount. So the less this document will contribute to the user satisfaction somehow. So the discount is based on the logarithm function and the rank position. For system A, if we look, this should be a free. Well, no, it's okay. For system A, it's here. So we have the first relevant document is relevance 2. So no discount because this is position number 1. Okay. Then the second relevant document in position number 2. Here we discount by the logarithm. And in this case, it's also no discount because we have base 2. When we move in position number 3, again, it's the relevance divided by the logarithm of the rank position. And the next relevant document is at position number 6. So it's 1 over logarithm 2 of 6. And we sum until the end of the ranking. Now you see that if we go with DCG, what we get is a score which is higher than 1. So 0.6 in this case. So that's why we want to normalize this score, again, for interpretability to range in 0, 1. And the way we do it is by considering the ideal run. So what is the ideal run? You take all the relevant documents in the collection. So if we go back to the exercise, you take all these documents here that are judged relevant and you sort them by their relevance label so that the highly relevant are at the top and so on. And what you will get, it's what is called the ideal ranking. And you compute DCG on the ideal ranking as we did before for system A. And basically you obtain the maximum achievable for that query. And this is your normalization factor. So DCG is basically divided by the DCG of the ideal rank. And this gives you a number between 0 and 1. And again, if we look at this example, system B is slightly better than system A. And this is because system B has some kind of partially relevant document that even if it's lower down in the ranking, it contributes to the final score. Now, if you remember, the decision was the opposite for average precision. So for average precision, system A was better than B. And it also average precision discounts for the rank position. So what's the difference? Here, the difference is basically that average precision is a bit more harsh in the way it discounts. And also, in NDCG, we have graded relevance. So we account also for the amount of relevance that each document brings to the score. Now, if we go back to the computation at 5, again, it's the same as before. It's just that we stop at rank position 5. And what we can see is that now system A is better than system B. So again, if we focus only on the top, system A is better because it retrieves documents higher in the ranking. Any questions so far? So there are different versions of DCG or NDCG. What you have seen, like in the slides, is the version from the original paper, where you basically consider the relevance weight, and then you normalize by the rank position and the logarithm. The base in the original paper, if I remember correctly, was 2 and 10. Defines the user patience. So if you use 10, you basically do not discount up to position 10. So you assume that the user is very patient and will look at all the documents up to position 10. Now, another version that you might see is this one, where basically the difference is in the discount function. So here is usually true, and you consider the rank position plus 1. So there is no discount at rank position 1 because it's logarithm of 2 over 2, but it starts to discounts from position 2. And another version is this one, where you, instead of looking at the relevance weight, you kind of take 2 over the relevance weight. This is to account for highly relevant documents even more. So you have an exponential function involved. So for reproducibility reasons, be clear on the version you use. And you might also have a look at these tools, Retrieval, PyRetrieval, and Track tools that you can use to compute all the measures, basically, that you had in your exercise. Any questions so far? Okay, so what about unjudged documents? As I said at the beginning, unjudged documents are treated mainly as non-relevant, but there are some measures that can deal with unjudged documents, or somehow they account for unjudged documents. One example is binary preference. It's bpref. It's a kind of extension of average precision with the idea of accounting for documents that are judged non-relevant. And not only considered non-relevant because they are unjudged. So there is a penalty here that counts basically how many documents that are judged as non-relevant are retrieved above a relevant document. And then you can see that the measure resembles a bit average precision because you have here the sum over the rank position of relevant documents. Here you normalize with the recall base as in average precision. And here where you compute the penalty, you take the minimum between the recall base and this number, which is the total number of documents that were judged non-relevant. So the recall base is the total number of documents that are judged relevant, and this is the total number of documents judged non-relevant. Usually, in reality, what you will have is that the recall base is lower than the number of judged non-relevant. And this is because in many tasks, you can find a lot of non-relevant documents, but very few relevant ones. So usually the normalization is with the recall base. And here is an example. So for this ranking, we have two documents here that are unjudged. And this is the computation of average precision as before. When we need to compute BF-pref, the way it works, it's basically consider the rank position of relevant documents. So we start here, and then we have no penalty, basically, because there are no unjudged documents at this point. We move to rank position 3, and now the penalty is 1/8, because we have one judged non-relevant before this document. Again, when we move to 4, the penalty is still 1/8. So it's somehow kind of precision with some penalty. And when we move down here to 8, we can see that the penalty becomes 2/8 because it considers only the 2 that are judged non-relevant. So these documents here, they kind of do not contribute to the measure somehow. And you can see the final score. Now, if these two documents here were judged as non-relevant, you can see that the score goes a bit down. So somehow the measure tries to be a bit more lenient in the sense that if there are non-judged documents, it doesn't consider them as non-relevant, but adjusts a bit the score to this. So how do we choose the measure? Well, I don't think we have time to go through this, but the idea is that the measure you want to use has to be tied, as I said at the very beginning, with your research question and with your task. So, and it also, like, what you can consider is whether you want a set-based evaluation versus a rank-based evaluation. Do you care about the ranking? And how much do you care about the ranking? So if you consider a measure computed at cutoff K as, for example, precision or recall or reciprocal rank as well, these are kind of rank-based measures, but up to the cutoff, they do not care about the ranking. So this is a very naive solution. While if you really want to consider the ranking, then average precision or NDCG are good choices. And again, there is a difference in the way average precision and NDCG handle the discount. As we saw previously, in some cases, average precision can be a bit more harsh in the way it discounts relevant documents. And then also something you need to think about is whether you have multi-graded relevance or binary relevance, whether it makes sense to use NDCG depending on the task. How many relevant documents do you have? If it's only one relevant document, then maybe you can use simple measures. You don't need to go with average precision and so on. And all these measures, they kind of do not account for the user behavior and the user experience. And that's what we'll see in the next part of the lecture. So all these measures, they are designed somehow to measure the user satisfaction. But do we really do this with average precision or NDCG? How is the user experience involved in these measures? And the idea here is to think about the user model so that we try to make these two components, the system focus and the human focus, a bit more close. Because one of the main criticism of IR evaluation is that it's not realistic and it's very far from what is the user experience. So by thinking about the user model, we want to account more for the user in the track style evaluation. So maybe we can do this very briefly, a couple of minutes. You can discuss in groups, how should the user model look like? So what would you account when you want to try to model the user behavior? So any comment? Anyone that wants to share something about the user model? If you have to say something like, how would you expect the user will browse the ranking? So I'll tell you what has been proposed so far. So average precision. What's the user model behind average precision? We assume the user will start position number 1, will examine the document at position number 1, then the user will decide either I abandon this search or I go to the next document. The user examines the next document, and again, either I leave this task, this search, or I'll go to the next one. So the user will scan the document from top to bottom, and will examine each document until the end. And at each rank position, we can define the user satisfaction or the probability that the user is satisfied at a certain rank position N. And if the user is satisfied, then the user will leave the search. So a very simple user model. And if we formulate the expectation in terms of precision, this is precision computed at relevant documents, otherwise it's 0. Basically, what we obtain is a formulation that somehow resembles average precision, apart from the fact that here we don't have the normalization of the recall base. So if this probability of the user satisfaction is 1 over the recall base, what we have is exactly average precision. So another way to explain average precision is, okay, we have a user that goes from the top to the bottom of the list, and with probability 1 over the recall base, the user will abandon the list at rank position N. And this happens only when there is a relevant document. So the user will never exit when there is a non-relevant document. And this also assumes that the user somehow has knowledge of the total number of relevant documents, which is not the case. But the model was justified by saying that this probability represents the probability of satisfaction given a population of users. So it's somehow an average over the population. But this is one of the criticisms behind average precision, for example, that the user model is not very realistic. So another measure was proposed to address this criticism is rank bias precision. Again, we have a ranking. The user will start from the first document, looks at position number 1 always, and the utility in this case is 1 because there is a relevant document. Then the user basically will account for this utility, and the user decides, okay, I leave this ranking, this search with probability 1 minus p, or I'll go down the list with probability p. And now I have another relevant document in position number 2. So utility again, and we somehow consider the utility, but we also consider that this is at position 2, so we discount somehow this utility by the probability of the user going down the list. And if we go like this, so the user will examine position number 3 with probability P per P, and this is because as an exited before. And if we go down the ranking like this, what we can, if we generalize this at position number I, the user will visit that ranking with probability P I minus 1. So again, we consider the utility somehow discounted by the probability that the user will actually examine the ranking up to that point. We'll sum up all the utility, and this is what we get. So the expected utility for that user, where this is the length of the ranking. So for each rank position, we sum up our utilities, but we also consider a discount based on the probability. Now, this P, this probability, is called the user persistence and somehow represents how the user is willing to go down in the ranking. And RBP is what we saw before, this part here. But then we have a normalization factor to make the measure ranging in 0, 1. And how does the normalization work? We assume that we have an infinite number of relevant documents, and we fill our ideal ranking, let's say, with relevant documents, this infinite number. Now, if we compute this sum, this will converge to 1 over 1 minus P if the probability is below 1, as it is. So that's why we have this normalization factor. So RBP does not account, if you look at this equation, for the total number of relevant documents that are judged, the recall based. But on the other side, to normalize the measure in 0, 1, you have to assume that you have an infinite number of relevant documents. And some of the criticisms that were posed for this measure is that this persistence of the user, so the probability that the user goes down in the ranking, does not depend on the relevance of the documents, on the rank position, and also on the documents that the user previously examined. So it's a very simple user model. If you have to decide on how to set this p-value, this persistence or patience of the user, usually the default, it's around 0.8. It means that the users will have a 10% probability to go to the second page. So these are somehow patient users because at least they go down the ranking. While if you set a very high P, like 0.95, the probability to enter the second page, sorry, this is wrong, I will fix it, but it goes very low. So the way you kind of represent different types of users, it's based on the probability or the persistence. Now, again, this is a simple model because as you see, this probability or persistence is independent from many factors that actually affect the user experience. And this model, sometimes it's called as a position model. So a position model basically assume a user that scans the documents from top to bottom. At each rank position, the user gets some utility and decides, okay, I'll go out or I go to the next document. And every time the user visited the document, the user got some utility, and like this until the very end. And then it's like some gain that you have at each rank position. multiplied by a discount function. Now, LDCG assumes this position model where the discount is depending on the logarithm and the rank position. And RBP, again, assumes this position model where the discount depends on the persistence. Now, if we look at some flip-flop data, here you can see the discount functions of NDCG and RBP. And in green, this is the real probability from the log data. So you can see that it's pretty realistic. But still, one argument is that now in this example, the first document here, it's highly relevant. And then the user goes down to the second one. But you can think about this. If the first document is not relevant instead, what the user will do, he or she will probably go to the second document with a higher probability because the first one was not relevant, right? So the user will search for something else. And this is the idea behind expected reciprocal rank. So again, we have a user that starts at position number 1, but now the probability to go out, which is defined by R, depends on the rank position and the documents in that position. So every time that the user scans the list, you will have a different probability to continue or to go out. And at the very end, what you will have is that the probability that the user stops or leaves the search at a given position K, it's basically this equation that you have here at the bottom. So the probability that the user will not leave, 1 minus R, multiplied by the probability that the user will leave at position K. And these values are basically defined on the relevance of the documents. So one proposal is to use this function here, that if you remember the different versions of NDCG, it's very similar to one of them. So the user, if it has, it's on a high relevant document, will go out with very high probability as the user is already satisfied, and it will go on with very low probability. And again, you can compute this throughout the ranking. What you will see is that if a user is on a non-relevant document, the user will not go out, but it will examine the next one. And again, the expected utility of a user being satisfied when a user stops at position K is basically computed by this sum, where you have the probability of the user stopping at position K and this utility. And again, we want to discount the utility of the user with the rank position. And in expected reciprocal rank, they took the reciprocal rank. So there are other measures, and I'll go fast, but you'll have the slides. The main idea behind time-based gain is that you want to consider the time, as the name suggests. And how do you do this? So you have this gain here. This is how much the utility your relevant document brings. And this is the time you spend to examine the list up to position K. So the main idea behind this measure is the more user effort, the more time the user needs to go through the list, the more we want to discount the gain that relevant document brings. So it's like discounting by the rank position, but also considering the time the user needs to go to that position. And then We have other types of user models. So what we have seen so far, it's a user model or a model that scans the document from top to bottom, but actually we can also consider users that jumps through different documents and go back and forth, skips some documents, and also revisit documents that they have already seen. And we can model this behavior with a Markov process. And what we can do, we can consider the steady state or invariant distribution of the Markov process in the sense that we consider a user population or a long term. And the measure will actually be this steady state or invariant distribution multiplied by precision on relevant documents. So somehow I discount the precision as in average precision by this probability to see the user in that position on the long term. And there are also many other user models that are more comprehensive in the sense that they try to define a general user model that can describe many different measures. So there were a lot of topics that were not covered today, but the good news is that there is this book on advanced topics in information retrieval, which is coming soon. So there is a chapter there on evaluation that you can check. And about other things that I didn't cover today, you have some pointers here. So statistical tests, it's important, and it's also part of SIG-IR call for paper guidelines. So think about it. Think about, is the difference that I see when I compare two systems actually real? Does it matter, or is it due to some random fluctuations? There is online evaluation, usually done through A/B testing or interleaving. So one thing is when you do the offline evaluation, what we have seen today, but there is a lot more work on trying to compare these systems once they are deployed online. And then evaluation for recommender systems has some specific challenges. For example, just to mention one, the way you split the training data in training, validation, and test will affect your evaluation results. There are many other aspects you can consider in evaluation. This is also relevant for recommender systems, as was mentioned in the previous lecture. So you might want to consider also novelty, diversity, credibility, and many other aspects. And finally, what about large language models? So can we use large language models to replace our annotators to generate relevance labels, because it's so costly, right? Is this a good idea or not? I guess we will find this out in the near future. But that was it for today. So if you have any questions, feel free to come and ask.